the plane wave expansion method. In the last lecture, we converted Maxwell's equations into Fourier space, and this method, once we understand this convolution matrix stuff, really just falls out, and it's a very simple implementation of Fourier space Maxwell's equations. It is very, very popular for calculating band diagrams and dispersion of structures, and it usually leads to a matrix equation solved as an eigenvalue problem. So we're calculating modes that can exist in some kind of structure. I've never, well, I shouldn't say never, but I rarely see this used for any kind of scattering analysis. It's always some type of modal analysis. So that's what we're going to derive, and that's the traditional plane wave expansion method. Very quickly, we can go from the matrix equations we had from last lecture and formulate the basic eigenvalue problem. And I'll step you through 1D, 2D, and then at the very end, as a bonus, I'll also step you through an efficient 3D plane wave expansion method. We'll concentrate in this lecture on a 2D plane wave expansion method, discuss some implementation details. I'll very quickly introduce calculating band diagrams, and then also calculating index ellipsoids or isofrequency surfaces. That will be brief, and then I'll illustrate that through an example, and I'll step you through every little step of calculating a band diagram of a bandgap structure. Then as bonus sections, I want to talk about some problems and some solutions and some neat things that we can add to our plane wave expansion method. One is a problem that I call band crossing. We'll get to that. Another one is a really neat technique to boost the speed and performance of the plane wave expansion method called the reduced block mode expansion technique. And then very last, we'll talk about an efficient, how to formulate an efficient 3D plane wave expansion method. So here we go, formulating the basic eigenvalue problem from the plane wave expansion method technique. Last time, we converted Maxwell's equations to Fourier space and then wrote those in matrix form, and we ended up with these 6 equations. And we remember that these K matrices are diagonal matrices that contain the components of the wave vectors associated with all the spatial harmonics down the diagonal. These lowercase bolded letters, in this case UZ, these are the Z components of the magnetic component of the plane wave harmonics. So this is a column vector of amplitudes of these harmonics. In this case, the amplitude of the Z component of the magnetic fields. S's are the electric fields, are also column vectors. And the big, most difficult matrix was these epsilons and mu's, which were convolution matrices. They're full matrices. But we ended up here. We can take these 2 sets of equations, and we can write each set of 3 in block matrix form these 2 ways. So now what we have, this single epsilon is a convolution matrix, and now we put it into a big tensor, if you will, composed of convolution matrices. Our K matrices come together, and this really was the curl operation, but now actually happening in Fourier space. Again, a curl operation in Fourier space, and another block matrix of convolution matrices. So we can write this in a shorthand way. These curl matrices, if you will, in Fourier space is really a cross product of K with this vector. So these big square matrices, we're going to write this way. This column vector of column vector, since it contains an X, Y, and Z component, we'll write it as a lowercase bold u with an arrow on the top to remind us that it has the X, Y, and Z components. This block matrix of convolution matrices we'll write as a bold epsilon with square brackets around it. And then this final last column vector of column vectors we'll write as a bold S with an arrow over top of it. So we can take both of these block matrix equations and write them a little bit more compactly. And here's the substitutions that we made. Now we want to derive a matrix wave equation. So if the 2 equations on the previous slide are essentially the curl equations, we know that we derive a wave equation by essentially substituting one into the other. So we'll take this first equation and we will solve it for u. These are the amplitude coefficients of the magnetic field part of our spatial harmonics. We solve it for u. We end up with this equation. Now we'll take this expression for u and plug that in up here to replace u. And what we have is a big ugly matrix equation now that only contains s. So do a little bit of algebra and simplify it down. And here we are. This is the fully three-dimensional matrix wave equation for the electric fields. So this really is a three-dimensional eigenvalue problem, a generalized eigenvalue problem. We write a generalized eigenvalue problem this way, where suddenly we can have a big square matrix on the right-hand side. So if we look at this matrix equation we derived on the previous slide, we can see that A is simply the k-cross matrix, backward divided by this block matrix of convolution matrices, times this curl matrix again. B is our block convolution matrix of the permittivities. Our unknown x is S, which are our electric field components. And our eigenvalue in this case is minus k0 squared. And so we simply would construct A and B using these two equations in MATLAB, and we would call Eig, and out would come all of the eigenvectors and the eigenvalues. Now, just to foreshadow what we're going to do at the end of this lecture, we have what is a 3x3 matrix equation. Notice the unknowns here. S has three elements to it, an x, a y, and a z. It's possible to reduce this 3x3 formulation down to a 2x2, so it's literally half the size and saves you a lot of computation. It's the most efficient, and we'll save that for the very end as a bonus section. But we could solve this. We get the correct answers. It's just not as efficient as it could be. And we're solving a fully three-dimensional problem. We are calculating modes in a three-dimensional unit cell. Now for this class, we're going to implement the plane wave expansion method for two-dimensional problems. It's much faster, and everything that I want you to learn is still there in a two-dimensional code. I want to remind us again, what is a 2D device? And here we're talking about a structure that has periodicity in two directions. So we have periodicity in X, we have periodicity in Y, but in the Z direction, it's infinitely extruded. So remember, there's really no such thing as a two-dimensional simulation. Everything is a three-dimensional simulation. Just when we only use a two-dimensional set of data, that third dimension is infinitely extruded. Further, we're going to restrict propagation to be within this plane. And so when we talk about a 2D plane wave expansion method, this is really what we're modeling, and we're asking the question, what modes can exist inside that structure? So there's no source, we're just asking what configuration of the fields can exist in this structure. So we want to reduce our three-dimensional equations to two-dimensional. Well, if it's infinitely extruded in the third dimension, up to now we said any derivative in that direction has to be zero. Well, our derivatives really became these K matrices, and so if there is no propagation in the Z direction, then our K sub Z matrices have to be zero. Well, then we set that to zero in Maxwell's equations. And just like before, we see now Maxwell's equations separate into two distinct modes. One we'll call the E mode, and one we'll call the H mode. And I color-coded them so that the red equations are one mode, and then the blue equations are another. So when we separate them, here are our two modes. So now we want to derive matrix wave equations for the two-dimensional case. So we'll start with the E mode with the three equations we had from the previous slide. We'll take the the last two equations, and we'll solve them for u sub x and u sub y. And we get these two expressions. Now we can take these expressions for ux and uy and substitute them back into the original equation, into the first equation. And what we'll end up with is a matrix wave equation with just s sub z in it. So we turn the algebra crank, and this is where we end up. So this is our final generalized eigenvalue problem, just in terms of sz. Now remember, when the three-dimensional case, our unknowns had three components of them, x, y, and z. Now we only have one unknown component. So this is a lot faster, a lot more efficient. Our matrices are 1/9 the size for 2 dimensions that they would be in 3 dimensions. Well, we can do the same thing for the H mode, and here is our matrix wave equation for the H mode. And this shouldn't be surprising, but notice the only difference is mu's and epsilons are swapped, s's and u's are swapped, and mu's and epsilons are swapped. Other than that, it's really the same equation. This is rarely done, but I'll step you through an efficient 1D formulation. For one-dimensional problems, we have 2 different dimensions that are infinitely extruded. We're really talking about the same types of structures that we were modeling with the transfer matrix method, where we had these infinite slabs. So in the one-dimensional case, we can set both kx and ky equal to 0, and we'll retain the kz component. So if we set both of these to 0 in Maxwell's equations, here where we end up. Right away, we can see that s sub z and u sub z are always 0. So in other words, these modes have no components in that longitudinal direction. We also see that Maxwell's equations decouple into 2 independent modes. One we're going to call the EX mode because it'll be polarized in the X direction, and the other we'll call the EY mode because it will be polarized in the Y direction. Now, for isotropic materials, something being polarized in X versus something being polarized in Y, it really doesn't matter. We're going to get the same solution. So if we derive matrix wave equations, which we've done up here, so here's the matrix wave equation for the EX mode, the matrix wave equation for the EY mode, notice it's really the same equation. So we can just write it this way with just an S, and that could be an S sub X or an S sub Y or whatever. And that is our eigenvalue problem, generalized eigenvalue problem for a one-dimensional stack of slabs. Now let's very quickly go through some implementation details, and then we're going to be following this up with an example that does even more details. So we went through this in a previous lecture when we talked about periodic structures, so let me repeat this. We're eventually going to calculate band diagrams and index ellipsoids, but let's look at the plane wave expansion method from a user's perspective. And we're going to wrap a black box around this algorithm that solves Maxwell's equations. So what we need to give it as input is a description of the unit cell. That's our mu's and epsilons. We also need to give it a block wave vector, which has 2 pieces of information. It has the direction of this block wave going through our lattice, and it also has the period of that wave. So it has both direction and spatial period. So the 2 bits of information that our plane wave expansion method needs is a unit cell and a block wave vector. And we're essentially asking the question is saying, given this infinite lattice with this unit cell, what waves travel in this direction with a certain spatial period? What does that? Then the plane wave expansion method does its stuff, and out comes the answers, and there's always an infinite number of answers. Remember, our eigenvalues come out as k0 squared, so these are the frequencies of the modes, all possible frequencies that have modes consistent with what we've described as the input to the problem. The eigenvectors are the pictures of the fields, and if we're solving this in terms of the magnetic fields, our eigenvectors are a picture of the magnetic fields that we could image to the screen and see the modes. Now, in reality, In physical reality, there's an infinite number of these modes. But we know the energy just tends to be in the lowest order few, and if we've only chosen, let's say, 500 spatial harmonics, our matrices will be 500 by 500. We can only calculate 500 modes. Those other ones we're just not able to resolve. But hopefully, the energy out of these higher order modes is negligible. And then we know we've chosen enough spatial harmonics. So let's talk a bit about choosing how many spatial harmonics we have. A rough rule of thumb is about 10 spatial harmonics for every wavelength wide your unit cell is. So given a picture of a unit cell, we can roughly make a really good guess as to how many spatial harmonics we'll need. But remember, the rigorous way to do this is to look for convergence. We will keep cranking up the number of spatial harmonics until the answer no longer changes that much. We call that convergence. But just looking at a unit cell, we can make a pretty good guess as to how many spatial harmonics we'll need. So let's do that. Let's look at this unit cell, and what we see is a uniform bar going left to right. Well, going left to right, there is no modulation in the material properties, so in fact we only need one spatial harmonic in that direction. If we look vertically, we see something that has low index contrast. It's a pretty thick bar. Maybe we could get away with only 7 spatial harmonics in the vertical direction. Now let's look at the same thing, but with a really narrow bar. We know very fine features, impulse functions, have a lot of frequencies in their Fourier transform. So in order to resolve this thin bar, we're probably going to need more spatial harmonics in that y direction. Is 15 enough? Maybe, and we have to look for convergence to determine that. It's still uniform in the horizontal direction, so we still only need one spatial harmonic in that direction. Well, if we have the same exact thing as our first case, but now rotated 90 degrees, then we would probably want about 7 or so harmonics in the x direction, and we only need one harmonic in the vertical direction because there is no modulation of the material properties. It's perfectly uniform in the vertical direction. If it has fine features horizontally, well, we need to add more spatial harmonics. Well, what if we have these thin little bars in both directions? Well, we probably need, let's say, 15 harmonics in both directions. Wide bars in both directions, we could probably get away with fewer spatial harmonics. So I might start with 7 by 7. Well, what if we have something that looks like this? Well, in the vertical direction, it's a bit wider. It's kind of like the wide bar case that we had. And I would probably use maybe 7 harmonics. But it's looking more like a narrow bar in the horizontal direction. Not quite as bad as what we saw over here, but still more narrow. So I probably would want to use more spatial harmonics in the horizontal direction. And now you get the pattern. So in the horizontal direction, we have this really thin bar. We need high spatial harmonics. Thick bar, vertical direction, 7 harmonics. Now if we go to really high index contrast, it's still uniform in the horizontal direction. We only need one spatial harmonic. But because it's high contrast and a narrow bar, now we probably need even more spatial harmonics in the vertical direction. Nice wide circle, low index. We'll use the same number of spatial harmonics in each direction, 7. When we go to high contrast, we need a little bit more. Maybe we need 21 by 21 harmonics. Little circles with low contrast, that's kind of an impulse function. We probably need a lot of harmonics as well. Then if we do the same thing but with really high contrast, well, now we need even more spatial harmonics. Anyway, this is the pattern. So the number of harmonics I have listed here are not absolutes. It's just how you can make good guesses as to how many harmonics you'll need based on what the unit cell looks like. But the true way to do this is to look for convergence. You keep using more and more spatial harmonics until the answer no longer changes. So we solved our eigenvalue problem. Our eigenvalues come out as k0 squared, or depending how we formulated it, maybe negative k0 squared. So we'll get rid of the negative sign, and we'll take the square root, and we have our k0s. The k0 is frequency divided by the speed of light. That while it's meaningful, it's not as meaningful as it could be. What a really meaningful number would be is a over lambda, because we can use this to scale our device to any frequency or size that we want. So we want to normalize these frequency eigenvalues to be a over lambda. Well, here's how we do that. We'll take our eigenvalues, which are k0 squared. We'll take the square root of it. So now we just have a k0. We'll multiply by the lattice constant a, which we normally set to 1, then divide by 2 pi. And usually on band diagrams and things, they write the normalized frequency this way, but in fact, this really is a over lambda naught. So given the position of a band or some feature in the band diagram, we'll immediately know how to scale the device to operate it at whatever wavelength or frequency we want. So here's the flow of calculating band diagrams and how it works. Remember, we have an example coming. So the first thing we'll do is, just like we've done for other methods, we will build our unit cell on a grid, a very high resolution grid, because we're going to need to Fourier transform these. Well, we Fourier transform them, and we construct our convolution matrices from them. Next, we have to choose all of the different block wave vectors that we want to run the plane wave expansion method over. Once we have that list, now we're going to set up a loop that iterates through that list. So for every value of beta, every block wave vector, we're going to repeat this section of code. The first thing we'll do is we'll build our K matrices. So these are diagonal matrices where the X and the Y components of the wave vectors associated with each spatial harmonic will run down the diagonals. Given these and the convolution matrices we calculated outside of the loop, now we can build our eigenvalue problem. And we use one of two equations depending which mode we're talking about. So we have the E mode or the H mode. So now we have our generalized eigenvalue problem. We can solve that, and that's just a call to Eig inside MATLAB. Our eigenvalues come back as k0 squared. We really want this to be a over lambda, so we'll take the square root of our k0 squareds, multiply by a over 2 pi, and this quantity will be our normalized frequency, which is a over lambda, which is very useful for scaling. So we record that data, and we go back up to our next value of beta. And when we're done, we're finished. So for each block wave vector in this list, we will now have a full set of eigenvalues, or eigenvectors even if we calculate those. Most of the time we're just interested in the eigenvalues. And we'll have a bunch of eigenvalues for each one of those block wave vectors. So let's talk a little bit more about photonic band diagrams. As we discussed in the periodic structures, band diagrams are very fast to calculate because they implement a single unit cell. So they're very rapid, and we can get a lot of information from that. Even though all lattices of interest are of finite size, the plane wave expansion method makes it seem infinite, but we can still get really useful information. So here's how they're constructed. The horizontal axis is actually our list of block wave vectors. Typically what we do is we construct an irreducible Brillouin zone. We label the vertices, which are called key points of symmetry, and rather than iterate through every single point within this volume, which would be a whole bunch of points, we're just going to set a line path somehow traversing all of these key points of symmetry around the irreducible Brillouin zone. So we'll go from U to X to gamma to L to K to W, and sometimes even we might go back to U. So we take this line path and we stretch it out, and in fact that becomes the horizontal axis in our band diagram. And so the list of block wave vectors that we construct at the beginning of the code might have 200 different values of beta that iterate along this axis. And in our example, we'll talk a little bit more about that. But for each block wave vector, if we're sitting here, for example, we plot the eigenvalues, the scaled eigenvalues, along the vertical axis. So all the eigenvalues we plot vertically. We move to the next block wave vector, we plot them vertically, and so on. And if we do that with enough points, we form these bands. Unfortunately, in these recordings, I can't play the movie, but what you'll see is the block wave vector here, and this animates as we're building the block diagram. So as we move along the horizontal axis and fill in the eigenvalues, you'll see this block wave vector. It always starts at gamma. At this point, it ends at u. We'll see that block wave vector traverse over to x, back to gamma, up to L, down to K, over to W, and up to U. So we finished our short discussion anyway of how to calculate band diagrams. Now we want to generalize that, and you'll see that calculating index ellipsoids or isofrequency contours is just an extension of calculating band diagrams. On this slide, I want to point out that we are missing information in the band diagram. In a band diagram like this, remember, we are marching around the perimeter of the irreducible Brillouin zone. But in order to know everything about this lattice, we in fact need to iterate through this entire area within the irreducible Brillouin zone, not just march around the perimeter. So we're missing information. So what are we missing? Well, if we draw the entire Brillouin zone, and now imagine we set up a double for loop, and we loop through this area, and for every point in the Brillouin zone, we calculate a stack of eigenvalues. In this case, they would come in and out of the board. So if we take that and turn it upright, we end up with the diagram on the right. So this plane on the bottom is the Brillouin zone. And for every point, we'll come up here and plot a discrete eigenvalue. And if our points on within the Brillouin zone are spaced close enough, we see that all these points here form bands or sheets. So this really is the full set of information having marched through the entire Brillouin zone. Here, we're not missing any information, so we would call it the complete band diagram. Okay, so let's grab the first order band, the first sheet. So now imagine we have a plane. So this is our frequency axis, so we can choose a plane with a constant frequency that slices through this sheet. The intersection between that plane and this sheet is an isofrequency contour. And in fact, we're drawing these down here. Each one of these is for a different frequency sheet. So we're moving this sheet, if you will, up and down and drawing where it intersects with this band. And we see we get different isofrequency contours depending on our frequency. Now let's look at the second sheet. And we come over here and we'll also intersect it with a plane. And when we do that, we get isocontours that we're showing down here. So now let's look straight down on just those isocontours. And here's what we have. And we would also interpret this as our index ellipsoids. Now notice with ordinary materials, isotropic, anisotropic, we have circles and ellipses. Now that we have a periodic structure, these index ellipsoids can take on other shapes, and we'll learn in the follow-on class of this that lets us do some very interesting things. So now I want to step you through step by step calculating a band diagram for a two-dimensional electromagnetic bandgap structure, and we're going to go use some of the theory we already discussed, but break it down into details and put numbers to it. So the first thing we need is our lattice. So here's a portion of the lattice. Since we're drawing multiple unit cells, we'll call it the extended lattice. If we assume this is infinitely periodic, we can just talk about one unit cell and use periodic boundaries all the way around. And since the plane wave expansion method decomposes into a Fourier series, it's just inherently having periodic boundary conditions all the way around. So we give this some properties. Lattice constant of 1, so it's a square unit cell with side length 1. This radius is 0.35 times A. and we'll have air in the middle here in this hole, and a dielectric constant of 9 out here in the green region. So we want to calculate the band diagram associated with this lattice. The first thing we need to do is calculate the lattice vectors. So maybe we start with the direct lattice, and we see we have these the primitive translation vectors, which in this case are the same as the axis vectors. So the first one is just the lattice constant times the unit vector in x, and then the second one is the lattice constant times the unit vector in y. So this makes sense. Then we can calculate the reciprocal lattice vectors, and we get capital T1 now as being 2 pi divided by the lattice spacing in the x direction, and the second lattice vector for the reciprocal lattice is 2 pi over a in the y direction. So this on the right hand side is the reciprocal lattice of our direct lattice, and the direct lattice is the thing that we can touch. From there we need to identify the irreducible Brillouin zone. So at this point, just focus your attention on the circles. So here's a circle, and here's all of its neighboring circles. So what we do is we pair this center circle off with each of its neighbors one at a time. So we look at its first neighbor, and we're going to draw a dashed line which separates the region of space that's closer to the second point than this, closer to this first point than the second point. So in fact, it's a dashed line that intersects these two circles. So everything below this line is closer to the center circle than this neighbor. Well, now we come out here to this neighbor, and we draw another dashed line that bisects in the middle of them. So everything on the bottom side of this line is closer to our center circle than the outside circle. Now we move to the next neighbor. We have another intersecting line. And we keep going around, and these blue dashed lines show all the intersecting lines. So the Brillouin zone is the region of space closer to the center point than any others. So in fact, we get this square region that is closer to that center point than anything else. And it turns out that our the primitive translation vectors of the reciprocal lattice are pointing right along these sides. So that is our Brillouin zone. We constructed a unit cell in reciprocal space. Now we want to identify the irreducible Brillouin zone. So we have our direct lattice, and we constructed the Brillouin zone. On the last slide, we constructed the Brillouin zone. Well, notice the unit cell and the lattice itself has left-right symmetry. It has mirror image symmetry, left and right. So that means we only have to calculate numbers in half of the Brillouin zone, because we can just mirror image all of the data from here over to the other side, and we know everything about the unit cell. So we're down to half. Well, it also has up-down symmetry. We can fold this up and down, and it has additional symmetry. So in fact, we only have to calculate numbers on either the top or the bottom half. Combining that with knowing we only have to calculate the left or right half, we're down to just a single quadrant. And we can reconstruct all the data in these other 3 quadrants based on data we calculate here to know everything about the unit cell. Well, there's more symmetry. We can take this and rotate it 90 degrees. So there's still additional symmetry. And in fact, what that comes out to is we only have to calculate numbers within this triangle of the Brillouin zone. We can mirror image the data here up to this upper triangle. Then from this quadrant, we can mirror image that over to the left. Then all this data on the top, we can mirror image down to the bottom and reconstruct all of the data within the Brillouin zone. So this little region, we can't shrink this down any further. So that is the irreducible Brillouin zone, and that's where we need to focus our attention. The next thing we want to do is identify all the key points of symmetry. And at some point, I handed you out something that listed all of the Brillouin zones and the naming conventions for the key points of symmetry. And in this case, we're calling our key points of symmetry gamma, x, and m. Now, if this didn't have all the symmetry that it would need, maybe we'd have to also label this with a different letter and potentially all these different points if it was a really crazy looking unit cell. But for what we have, which is the most common, we really only have three key points of symmetry, gamma, x, and m. And we want to calculate these from the reciprocal lattice vectors. Well, gamma is always at 0. That's the origin. X, as it turns out, is just half of T1. So notice T1 is the full length of the Brillouin zone. Well, this distance is just half of that. So x is 0.5 times T1. M is now along the diagonal. So we definitely come over half of T1 and we go up half of T2. So that's how we calculate M. It's half of T1 plus half of T2. Now we have our three key points of symmetry, the positions in reciprocal space. So here's some actual numbers. For a lattice constant of 1, the primitive translation vectors of the direct lattice are this. Then the primitive translation vectors of the reciprocal lattice are this. So remember, this number is actually 2 pi over 1, or 6.28. Based on these two lattice vectors, we calculate our three key points of symmetry, gamma, x, and m. So we have numbers in here now. Now we want to calculate the horizontal axis of our band diagram. So we need a list of block wave vectors. Well, we go back to our irreducible Brillouin zone. We'll say, let's start at gamma, and we'll put a series of points between gamma and x, another series of points between x and m, then another series of points to go back to gamma. So this list of block wave vectors will start at gamma, go through a series of points to x, go through a series of points to m, and then go through a series of points to gamma. So here's what this actual array would look like. We're in 2 dimensions, so we only need an x and y component. Our first one's going to be gamma, because this is where we're starting. Then we're going to go all the way up to x, where we still have a 0 in the denominator, but a 3.14 in the numerator. So along this row are numbers that will steadily increase from 0 up to 3.14. So in fact, this is a whole bunch of vectors that gradually increase from gamma up to x. Now we're going to go from 3.14, 0, all the way up to 3.14, 3.14. So all the numbers in the top are 3.14. The bottom number here, or the y component of the block wave vector, will steadily go from 0 all the way up to 3.4. So in fact, this whole list of vectors are vectors that steadily go from x to m in the irreducible Brillouin zone. Then we're going to go from m back down to 0. So we have both components being 3.14 all the way to both components being 0. So in fact, both components slowly ramp down from 3.14 down to 0. And there may be, 20, 30, 40, heck, even 100 points connecting these key points of symmetry. But the point is, we come out with one array that's a whole list of block wave vectors that steadily goes from one key point of symmetry to the next in whatever path around the Brillouin zone that we choose. Now we use the plane wave expansion method. We set up a loop that iterates over our list. For each block wave vector, we calculate a whole list of eigenvalues. And in fact, here I've sorted them from smallest up to largest. So we go to the next block wave vector, calculate all the eigenvalues. Go to the next eigenvector, calculate all the values. We do this all the way across. Each block wave vector has a whole bunch of eigenvalues associated with it. And we come up with a big array of eigenvalues. Let's plot them. So here we see all of the points we had going from gamma to x, and we're plotting all of the eigenvalues that we've sorted. And we notice, as long as these points along the horizontal axis are placed close enough, we can see they really do form smooth, continuous bands. And that is the beginning of a block diagram. Well, we want to make it look pretty. The last one didn't look real pretty. And this, what we're showing in this slide, is very, very typical of what a good quality band diagram looks like. We want to give it a title. We want to show the bands as continuous bands. We want to label the key points of symmetry along the horizontal axis. And typically, you'll see vertical dashed lines marking where those key points of symmetry are. we normalize frequency, and for whatever reason, it's always written as omega times a over 2 pi c. C is the speed of light and a is the lattice constant. However, this really is just a over lambda naught, which is very useful for scaling. Also on the band diagrams is usually a picture of the unit cell, sometimes the extended lattice, and certainly at a bare minimum, a picture of the Brillouin zone with the irreducible Brillouin zone and all the key points of symmetry labeled. Without this, the person reading your paper or diagram really can't interpret the horizontal axis of your band diagram. Now I want to talk about a problem that I call band crossing. So we calculate our eigenvalues, we sort them from lowest to highest, and we plot them. So if we made all of the bands the same color, we would plot something that looks like this. Now notice, look at this green line. If we look at this little section, here's a close-up of that. We have the green band, which appears to do an abrupt bend here. And this happens because we've sorted our eigenvalues. And it just so happens this one's going to come, the blue line's going to come first, green line's going to come second, red line's going to come third. But in reality, if we look at this as we want to see continuous bands, this green line, in fact, should go straight and down. But it doesn't. So because we've sorted our eigenmodes without really paying attention to which band corresponds to which band, we get this band crossing problem, and that's an issue. So how do we fix this? Well, if we did fix it, here's what the data should look like. And a good example is this light blue line here. Notice it crosses a bunch of other bands, but we know it's its own band because it's a nice smooth continuous line, and it just crosses through everything else. And we can track this mode. This is one electromagnetic mode, and we can track this all the way across. So this is what a band diagram looks like if we've corrected the band crossing problem. Okay, let's think about how we do this. Normally, we construct band diagrams based on only the eigenvalues. However, if we need to figure out which band is which, we now also have to calculate the eigenvectors because we need to see a picture of the mode to see which mode goes with which mode. So if we look at our eigenvector matrix, we'll call that V, we will have a bunch of columns. All of these columns is a different mode. And of course, each one of those modes has an eigenvalue associated with it. So I'll just write the first column as V1, the second column as V2, and so on. I'm only showing 4 columns here, but real matrices have hundreds of columns. Now let's figure out a way to compare the modes with itself. And we'll define what's called an inner product. And we will take 2 column vectors, or 2 eigenvectors, which is not the eigenvector matrix. We're talking about the individual eigenvectors in here, which are column vectors. If we take the Hermitian transpose of 1, which instead of being a column vector, now after we've transposed it, it's actually a row vector. A row vector multiplying a column vector is a dot product, and it gives you one single number. Well, the most eigenvalue solvers will calculate modes that are normalized so that if we're comparing 2 different modes, we'll get 0. So in other words, the eigen modes are orthogonal. When m and m are equal, in other words, we're taking an inner product with itself, we'll get a 1. And these eigenvectors are normalized to ensure that this is the case. And this is a general property of eigenvalue problems, that the eigenvectors are orthogonal in this sense. So rather than do this one eigenvector at a time, let's take the eigenvector matrices. We'll take the Hermitian transpose of the eigenvector matrix and then multiply it by the eigenvector matrix again. So we're kind of multiplying it by itself, but we got this Hermitian transpose in here. Here's how we would write it as a big ugly square matrix. And if we did that, look at what we get, the identity matrix. Let's look at why that is. Well, in this first position, we have V1 compared to V1. So we're comparing V1 with itself. Well, clearly that's going to give us a 1 because it's the same mode. And in fact, if we look down the diagonal, we're comparing V2 with itself, V3 with itself, V4 with itself. So they're always going to give us 1s. Everything else, we're comparing two different eigenvectors. Well, orthogonality requires that all these multiplications will be 0. So if we have an eigenvector matrix, and we do this little operation, we should get the identity matrix, because the only thing that would give you a 1 from the orthogonality test, the dot product, is a mode compared to itself. Okay, so we solve the eigenvalue problem. We have this eigenvector matrix that we just talked about, and we have associated eigenvalue matrix. Each eigenvector goes along with an eigenvalue. This eigenvector goes with this eigenvalue. Third eigenvector goes with the third eigenvalue. Fourth eigenvector goes with the fourth eigenvalue, and so on. So suppose I took these and I scrambled the position. Same eigenvectors. I've just changed their order, but I still have the second eigenvector corresponding to the second eigenvalue, fourth eigenvector, fourth eigenvalue, first, third. So it's the same data in here as the first one. I've just scrambled the order of the columns. And this happens in many eigenvalue solvers, that we can't depend on the modes coming to us in the order that we want. Very often there's very limited control over that. And as your inputs change a little bit, the order of the modes can jump around. So this is one problem that leads to the band crossing. So let's take this eigenvector matrix and compare it to the scrambled eigenvector matrix. So we'll say V Hermitian transpose times W will give us this big ugly matrix. We don't actually have to do this. We can just simply do this operation. And what we get is essentially a scrambled identity matrix. Well, this tells us how we need to reorder it. We know in order to get the identity matrix here, we need this column placed over to the first column. Then we see a second one here. We need this column moved over here, and so on. So we can look at this matrix and see how to reorder things to restore the identity matrix. So here's that comparison matrix we had from the previous slide. We swap columns 1 and 3, so 1 and 3, because we want to bring this 1 over to this position. So we've done that. We've swapped columns 1 and 3 now. Well, now we want a 1 in this position, so we actually have to swap columns 2 and 3. So we do that. And now we have 2 1s here, so that's great. We want our next one to be here, so we swap columns 3 and 4. And finally, we end up with our with an identity matrix. So we take this recipe of how we swap columns, we do it to our scrambled case, and that unscrambles the modes. We have our original V and lambda back again in the proper order, but we had to look at the eigenvectors in order to do that. Now here's reality. When we go from one block wave vector to the next, we don't have exactly the same modes. They're very close, hopefully, especially if the change in the block wave vector is small. So let's say we have a very small change in the block wave vector. We're going to take the original eigenvector matrix with Hermitian transpose. We're going to calculate the new eigenvector matrix with a slightly different beta, and we compare all the eigenmodes. And what we see is that we no longer have something that would be the identity matrix, but we do see something that would be close. We have very large dominant values and then very small insignificant values. So I highlighted the large values in 1, but following the same procedure that we had with that scrambled identity matrix, we can see this and know how to unscramble it. Now, when we have larger steps in beta, these large values will be a little bit smaller, and the small values are going to be a little bit larger. At some point, when the difference in our betas becomes so large, we might not know what are the dominant values here, and unfortunately we just have to go use a smaller value, smaller difference in beta. But anyway, what comes out of this are almost identity matrices, and we can still look at them in the same way and know how to unscramble the modes. So we start with this matrix. We see right away we want to put this dominant number over here. So we're going to swap columns 1 and 2, and we end up here. And then we see we want to swap columns 3 and 4 here. And now we have this very obvious almost identity matrix, and we have our recipe now for unscrambling the modes. So we would do that to the V prime, and now those modes will match up exactly with the modes from that first case. So here's the basic algorithm for handling the band crossing. Step 1, we will take the first point in our band diagram, that first block wave vector, and calculate all the eigenmodes. Then we move on to the second block wave vector, and we calculate all its eigenmodes. So when I say all the eigenmodes, this means eigenvalues and eigenvectors. Now we've calculated 2 sets of modes. We have 2 eigenvector matrices. We can calculate the orthogonality matrix. So that'll be if the eigenvector matrix associated with this is V, and the eigenvector matrix associated with the second block wave vector is V prime, here we would have V Hermitian transpose times V prime. And we get this orthogonality matrix, which is the almost identity matrix, but hopefully it's close enough we'll figure out how to unscramble our modes. And that's what we do in step 4. We figure out how to unscramble the modes. And then in fact we unscramble the modes of the second case to match to the first case. Then we move on to the next block wave vector, the third one. We'll calculate the orthogonality matrix, and we'll sort the eigenmodes now to match the second set. So we're always just using the set from the previous block wave vector. And we just repeat that through all of our block wave vectors. So we start off with the first one, and essentially we line up the modes of the second to match the first. We'll line up the modes in the third to match the second. We'll line up the modes in the fourth to match the third. And we go through our entire list of block wave vectors that way. Okay, that's the end of the story for band crossing and how to fix that. We're sorting the eigenmodes. Completely different subject now. This is a really cool technique developed by Mahmoud Hussein, and it's called the reduced block mode expansion technique. And this really can speed things up in the plane wave expansion method. Very cool technique. So suppose we actually wish to calculate the full complete band diagram. We have to divide up the Brillouin zone with a whole bunch of points. We might choose 80 points by 80 points, so that's 640 points total that we have to calculate. That's a lot of points. And each one of those points can take a very long time, particularly for a 3-dimensional simulation. And we very quickly become bogged down calculating these isocontours and bands. So what can we do? So we use the reduced block mode expansion technique. Here's how it works. First thing is we'll look at the Brillouin zone, we'll identify our irreducible Brillouin zone, and we'll identify the key points of symmetry that surround the irreducible Brillouin zone. So in this case it's the gamma, x, and m again. What we'll do is we'll go in and we'll implement the standard plane wave expansion method, but just at gamma, x, and m. So we will calculate an eigenvector matrix for the gamma point, and these are all the modes for the gamma point. We'll do the same for x, and we'll do the same for m. So these are all the full eigenvector matrices for those 3 key points of symmetry. Standard plane wave expansion method so far. Then what we'll do is we'll choose the lowest m order modes in these eigenvector matrices. We might choose the lowest order 5 or 6. So we go into these 3 eigenvector matrices and we pull off, in this case I'm just drawing the lowest order 3. So we take these and we build another matrix U, and we put in these lowest order eigenvector matrices from our key points of symmetry. And an important point here is that this matrix U does not have to be a square matrix. So in fact, it's usually much taller than it is wide because we're only going to retain so many eigenvectors. We want to reduce that number. Then what we want to do, once we've constructed this matrix U, which doesn't have to be a square matrix, we want to do a Gram-Schmidt orthonormalization on that. So we're normalizing this matrix according to that algorithm. Here's a small taste of how that algorithm works. We will look at the first eigenvector in the matrix U, and we'll divide it by its magnitude. So the magnitude of V1 will just be 1. Then we're going to look at the second eigenvector matrix. And what we're going to do, we'll notice this little expression here is the projection of V2 onto vector V1. So we are taking this vector V2 and subtracting whatever component of vector V2 lies along V1. So what we're going to be left with is a vector that contains no components at all in the direction of V1. So it's its own unique vector. So, and then we divide by the magnitude of that, so we get unit magnitude overall. So V2 now will not contain any components in the direction of V1 and have unit magnitude. For V3, I take that vector, I subtract whatever component is along V2 and subtract whatever component is along V1 and then divide by the magnitude. And this keeps going. So each vector, we're subtracting the projection from all the previous vectors. So in this case, all the vectors in the matrix U will be in unique directions and all have magnitude 1. That's the Gram-Schmidt orthonormalization. From there, we're actually ready to implement the reduced block mode expansion technique. And what we want to do is go in and fill in the entire area of the irreducible Brillouin zone now. For each point, we will build the standard plane wave expansion method eigenvalue problem. We don't solve it yet, but we'll build the matrix problem. That's very fast and not a problem. And depending whether we're in E mode or H mode, this will be our A. And we have a different B depending whether we have E or H mode. So for each point now that we're interested in calculating all the eigenmodes, we build but don't solve the standard plane wave expansion method eigenvalue problem. Then what we're going to do is we're going to transform into the basis of our reduced block modes. So here is A and B built from the standard plane wave expansion method technique. We will transform into the basis of our normalized vectors, U with the squiggly over it. And now we get a reduced A. And similarly, we get a greatly reduced B. So A and B matrices are much, much smaller. So here's how I visualize it in my head. We have this big, ugly square matrix A. We have U, which is tall and thin. It has multiple columns because we've retained a certain number of modes, but it's very tall. Now, when I multiply this big square matrix by this very tall matrix, but with some width, I get a matrix that is still the size of just U. So now I have a U transpose. In fact, it's a Hermitian transpose, so it's sort of a row matrix, if you will, multiplying this column-ish matrix. And what we get is a little tiny A prime. So this equation is really just drawing it in terms of the sizes of things. So the same thing happens to A and B. We start with really big, ugly matrices. We transform into this basis, and now we have very, very small A and B matrices. And we solve that as now a greatly reduced size eigenvalue problem that's very fast to calculate. So that's exactly what happens. We have this greatly reduced eigenvalue problem. We calculate potentially eigenvectors. We actually don't need these. Maybe if we're sorting out the band crossing problems, we'll need those. Or if we want to see the fields, we'll need those. But if we're just doing sheets and band diagrams, all we need are the eigenvalues. It turns out these are the same eigenvalues that we would get had we just solved the standard plane wave expansion method problem. But the eigenvectors are much different. If we wanted to recover eigenvectors that are in the basis of the original eigenvalue problem, we would just have to transform back. So here's the eigenvector matrix. from the reduced problem and we transform back to V. So now these eigenvectors would be consistent with the original plane wave expansion method. But if we're just doing band diagrams and sheets and things like that, we don't need to do this. We don't need the eigenvector matrix. We only need the eigenvalues. And nothing on this slide, but we repeat that procedure for every point in the irreducible Brillouin zone that we're interested. We build but don't solve the standard plane wave expansion method eigenvalue problem. Then we transform into this basis of the reduced eigenmodes. That greatly reduces the size of A and B. And we solve that eigenvalue problems. Then we record those eigenvalues. We go on to the next point, build the standard eigenvalue problem, transform into the new basis, calculate those eigenvalues. And we fill in the irreducible Brillouin zone or our band diagram doing that. And that's it. That's the reduced block mode expansion technique. And because A and B are so much smaller, it really buys a lot of speed and efficiency. Okay, on to an efficient three-dimensional plane wave expansion method. Before we get into this, I need to introduce you a little bit more to my notations and some special notations and matrix operations that we'll use. So, unbolded letters are always scalar quantities, or at least will be in this section of my notes. A bold capital letter is a big ugly matrix. That's not a row or column vector. It's a big ugly matrix, usually square, but could also be rectangular. A lowercase bold letter is a column vector. A lowercase bold letter with the vector symbol over it is a column vector of column vectors. And the arrow indicates that the constituent column vectors are actually x, y, and z components. We have vector information here. But this is still a column vector, just 3 times larger than either one of, or any one of the constituent column vectors. So that's the notation for the variables. Now we want to talk about operations and a little bit more about notations. So we have a capital bold letter, so we right away know that this is going to be not a column vector but a square matrix. And in this case, it's going to be a diagonal matrix containing all the x components of some vector A. AY will be a diagonal matrix containing all the y components of the same vector A, and A sub z is a diagonal matrix containing all the z components of A. So for one of the components, I could be x, y, or z. We just see we have all those components of A, and there'll be n number of those. We can write bold A with an arrow over it, and what we see is we have a block column vector. However, this overall is not a column vector. It has some width because AX, AY, and AZ are square matrices. So we have a block column vector of square matrices. It's important to realize that. Now we can talk about several operations. We can talk about the magnitude of A, which will return a single matrix very similar to like one of the components. So we will take this diagonal matrix and square it, take the second diagonal matrix and square it, take the third diagonal matrix and square it, add them all up and take the square root. Now since these are all diagonal matrices, we end up with a diagonal matrix. And each element will be magnitudes of the vector. We can talk about a cross product. If we want to do A cross some vector that we're not showing here, but here is that cross product operation. If we want to calculate a dot product, here's how we do that. We have an AX, an AY, and an AZ as a row vector. Now this is not, remember these are square matrices, so overall this is a rectangular matrix, but much longer horizontally than vertically. Now from standard vector calculus, we remember that A dot B equals B dot A. However, that is not necessarily the case when we're doing dot products with this vector matrix notation. The only time this holds is when all the components of the matrices A and B are diagonal. Then we can reverse the order, but otherwise we can't do this. And likewise, remember from vector calculus, A cross B equals negative B cross A. Again, that does not hold here unless all those constituent matrices are all diagonal. AX, AY, AZ, BX, BY, BZ are all diagonal. Then we can do that. In Fourier space, it turns out the only matrices that we deal with that are not diagonal are the mu's and epsilons, because remember, they're the convolution matrices and they're full. Okay, so next operation. We can write any vector as the sum of two orthogonal polarization vectors. So we have this final S, which is the x, y, and z components of our electric field. And we know we can always decompose a wave into two orthogonal polarizations. So that's exactly what we're doing. We will have a matrix here, which is a block column vector, not a true column vector. It's a column vector of square matrices that are containing all of the components of some unit vectors P1 and some unit vectors P2, and we'll multiply these by some coefficient matrix S1 and S2. So we're going to choose our polarization vectors so that P1 and P2 are orthogonal, and P1 and P2 are orthogonal to the K vector of that particular spatial harmonic. Remember, we've lumped all of our spatial harmonics into these matrices, P1, P2. So P1, P2, and K for each spatial harmonic are all orthogonal. So here's the analytical expressions saying just that. And here's what those expressions would look like in matrix form if we needed those. But the point is here, we can take a vector matrix and project it onto two orthogonal polarizations. So let's do that. Remember, here is our three-dimensional eigenvalue problem in terms of the electric fields, and we have this S, which contains x, y, and z components. We will take each one of these S's and write it as the sum of two orthogonal polarizations. Now, we have not yet reduced the size of this matrix, but we have expanded our field now into the sum of two orthogonal polarizations. Now let's talk about projections and eventually get to how we do these projections with our vector matrix notation. In general, we can project any vector A onto vector B using this equation. And if you've had vector calculus, that should seem familiar to you. If we're only interested in the magnitude of that projection, we can use a simpler equation. Well, in terms of our vector matrix notation, here's how we would write that projection when we only are interested in the magnitude of that projection, not the direction. So we'll just, for shorthand, we'll write a projection of A onto B with these little triangular signs. I'm not sure what they're called. So, but that'll be the shorthand notation for projecting A onto B, and here we're only interested in magnitude information. So suppose we have a vector matrix equation of this form. So x and y are both of these are block matrix column vectors, where each matrix element of those is a square matrix, and then big ugly square matrices A and B. Well, we can take this equation and we can project both sides onto vector P1. If we do that, we get this. Now notice we have this inverse B on the outside here. We really should have the magnitude inverse of P1 on the outside and on the left sides of both of these sides. However, the inverse magnitude of P1, since these are unit vectors, that's what the little hat means, it's just the identity matrix. In fact, we don't have to write those. They drop out of the equation. We can take this matrix equation and project it onto P2, and we get a new equation. Now, both sides of this equation, A and B, are 3 by 3 matrices. After we do this, both sides of each of these equations is 1 by 1. So we went from a single 3 by 3 matrix equation, block matrix equation, to two 1 by 1 block matrix equations. Okay. Recall this equation. We took our original three-dimensional eigenvalue problem, expanded the electric field into two orthogonal polarizations. Now we're going to take this matrix equation, we'll project it onto P1, and we'll project it onto P2. So we're going from one 3 by 3 block matrix equations to two 1 by 1 vector matrix equations. We can take these two 1 by 1 vector matrix equations, they both contain S1 and S2, and we can write these in block matrix form. And in fact, this is our final matrix eigenvalue problem. We went from a 3 by 3 block matrix equation to a 2 by 2 block matrix equation. So it's about half the size and a lot more efficient. And we also see it's a generalized eigenvalue problem. And here's what we just did. This is the reduced eigenvalue problem for electric fields. We just derived that. And we could have done the same thing for magnetic fields, and we'd end up here as the reduced eigenvalue problem. So this is how to efficiently handle three-dimensional problems. We don't need that original 3 by 3 eigenvalue problem. We've reduced it to a 2 by 2 eigenvalue problem, which is much faster and more efficient to solve.